This split screen highlights a common problem in Revit. On the left, a fully populated 3D architectural model. On the right, a 2D floor plan of that exact same space, where critical interior walls and floors are missing. Faced with this, the typical response is to start clicking. Users toggle categories, cycle through the Reveal Hidden Elements bulb, and adjust view settings at random, hoping the geometry reappears. This trial and error method fails because Revit is a dynamic rendering engine, not a static drawing program. Every view is the result of competing database rules. Whether an element is visible, partially obscured, or hidden is governed by a multi-layered hierarchy. This hierarchy follows a specific order of operations. Any setting located lower in the stack takes precedence over the global settings above it. To solve visibility issues quickly, we have to conceptually map this stack from the top-level defaults down to the individual line overrides. Applying localized overrides without a plan creates a fragile, unpredictable model. Mapping out the exact chain of command is the only way to ensure graphical consistency across an entire drawing set. We can visualize this process starting in a blank 3D space. Before any rules apply, we have a basic wireframe representation of a standard architectural wall. At the top of the hierarchy are object styles. This layer has the weakest override priority, establishing the baseline line weights, colors, and patterns for categories across the entire project. Because this is a global baseline, the line weight you set here dictates how the wall renders in every view by default. Layered directly beneath that are materials. This acts as a secondary global override, defining the surface textures and render graphics applied to the geometry. If a material is misconfigured, for example, if it is assigned 100% transparency, the element becomes globally invisible. This leads users to search for view-specific errors when the problem is actually baked into the material properties. Because object styles and materials are global, trying to fix an error at this level using local view overrides only hides the root problem and eventually causes project standards to drift. Moving down the stack, we reach view-specific controls. These settings allow model elements to appear differently depending on the context of the specific sheet or view. This layer introduces visibility and graphics overrides, or VG. This is the primary tool for overriding the global baseline within a single view. Unchecking a category in the VG menu negates the object style baseline for that view, completely removing the element from the display. Next is a layer that often causes elements to vanish without warning: phases and phase filters. If an element is assigned to the New Construction phase, but the view's phase filter is set to display Existing only, the Revit engine purges the element from the view. Crucially, phase filters execute before VG settings. Toggling categories in the Visibility Graphics menu will not bring back an element filtered out by its phase assignment. While VG provides flexibility for specific sheets, failing to align the model's phase data will override all other category settings, often leading to missing geometry. To target specific elements rather than entire categories, we use logic-based visibility. This introduces view filters. View filters use conditional rules to override graphics. Instead of changing every wall in the view, you can instruct Revit to highlight only the walls with a specific fire rating parameter. Because filters sit lower in the hierarchy than VG, the filter rule will overwrite any standard VG category settings. This creates a risk of unintended consequences. A filter designed to hide furniture might also hide structural elements if the parameter rules are too broad. While filters are essential for data-driven graphics, but their position in the hierarchy makes them a primary suspect when elements appear with the wrong colors or patterns. At the bottom of the stack, programmatic logic is replaced by manual, localized user actions. This starts with element overrides. Using override graphics in view on a single element severs it from its category rules, VG overrides, and parameter filters. Finally, we reach the most powerful tool in the hierarchy, the linework tool. The linework command ignores every other layer in the stack. When applied to an edge, it replaces the existing graphics with the chosen line style, regardless of any settings above it. Relying on manual overrides creates invisible rules. Other users working in the model will have no way to track or change these one-off graphical adjustments through standard menus. Manual tools are useful for final sheet presentation, but using them as a primary drafting method leads to an unmanageable model. The priority for rendering always flows downward to the most specific local override. Because of this, the logic for troubleshooting must flow from the top down. Instead of clicking at random, evaluate the stack layer by layer. First, verify global baselines, like object styles and materials. Next, check view contexts, phase alignment, VG toggles, and view filters. Finally, search for isolated issues, like manual element overwrites or line work. Understanding the visibility stack provides a structured path for troubleshooting. It replaces trial and error with a technical workflow that ensures every element appears exactly where and how it should on the sheet.